Okay, so yeah, I'm delighted to join you today. This is actually the shed where Undo started and where Mark, who'll be speaking shortly, had his second interview. His first interview was in the pub. And so in these strange times, I'm now back in the shed. So we think of software with this sort of productivity or velocity versus quality trade-off. If we're writing, I don't know, a game or something like Facebook, move fast and break things, we can be very productive and sacrifice lower quality. Or if we're writing the software that controls a nuclear power station, we're going to be very high quality, and we accept there'll be a glacial kind of pace of progress. But I think that's the old way we used to think about things. I think now we realize that actually you can do much better. And if the quality is high and our processes are good, and in particular, if we're testing thoroughly and we've got solid software, then our productivity can actually get better. And you put it the other way, what's worse for productivity than working on a code base where you make a small change, everything breaks, you don't know whether it's your fault or you just tickled something, some latent thing. One of the things in particular is the amount of testing that's being done. And I think these days, most software organizations run way more tests than they did a decade or two ago. I mean, even certainly 20 years ago, even perhaps 10 years ago, if you were doing any kind of automated testing, you were probably in the good half, right? And in fact, this probably shock most people who do things like come to these kinds of conferences, because we're probably all, some of the, we're, in the top sort of quartile or whatever, at least I would have thought of best practices. But there are still, I've encountered software organizations today still for whom a test script is a Word document that you follow the instructions and say do all the features work, and it's very manual process, and you have testers who are just like testing the software to see if it does what it's supposed to do. And then you might run, say 50 tests a week. I mean, these days running 50,000 tests per hour is not a lot. I mean, we run way more than that in Undo. I'm sure most of the people at the conference here run orders of magnitude more tests than that every hour. And if you just do kind of the arithmetic on what this means, is the large numbers of tests. I mean, in the old kind of manual testing world from decades ago, 50 tests a week, if half of them were completely solid and the other half were 99% reliable, by which I mean they when they fail 99% of the time, that's because the code under test is failing, right? The test is telling you what it's supposed to tell, and the other 1% is just, it's a sporadic failure. It's a bug in the test or in the test case. If you've got that kind of, you could live with that, right? Do that, actually do the maths, you get to 1 sporadic failure per month. If you're running 50,000 tests per hour, similar kind of makeup, you're going to get hundreds of thousands of sporadic, of spurious failures per month. Even if you're running 50,000 tests an hour, I mean, you might be, of course, orders of magnitude more than that, but even if you're running 50,000 tests an hour, and of your tests, 99% of them are completely solid, they never fail unless the device under test fails, and the other 1% only spuriously fail one time in 1,000, that's still hundreds of failures every month to investigate, hundreds of rogue failures. So just use these math to show that if you're running modern, very large amounts of testing, you really need to have totally solid tests, right? You can't tolerate even a small number of spurious failures. And if you do that, that's one of the key pieces to being on the top right of this quadrant, being both very productive and producing very high quality software. So something we call go green, stay green, right? Get your test suite reporting all green and keep it there. Actually, going green is the hard bit, right? Most software organizations get themselves kind of in a bit of a mess when you're just drowning under this, or you get this sort of background radiation of spurious failures, and it means you can't spot new ones, right? And so if you get in, most people get themselves when they're not in the place where they're green, and it's really hard to get there. Once you're there, it's not too bad. So the first step to get there is you have to exclude the flaky tests or the sporadics or whatever you call them. Sometimes this is controversial. People worry about losing coverage. Often they might worry that, well, if we exclude it, we'll never get around to fixing it. And my retort to that always is, if you're using your test suite as your to-do list or your bug prioritization process, then that's a problem, right? And you need processes in place where you can actually exclude things with the confidence that you are going to get to look at them when at the time that's appropriate. Having tests that you can't trust doesn't add any value to anybody. But then step 2 is you've got to fix the flaky test, right? It is no good just excluding everything that fails flakily and never coming back to it, because there's coverage that you need there. So how do you do that? Well, if you don't do that, you get what I think a lot of us are familiar with, is this ever-growing backlog of tests that fail spuriously, right? And the backlog just grows, and no one knows why they're doing what they're doing. And in there, these are canaries in the coal mine that we're stepping over, right? They're tomorrow's production outages or security breaches or data loss or whatever. I'm going to skip over this for time. So here's what we sometimes end up doing, right? Trying to get all of the conditions exactly as they were so we can reproduce the failure. What I'm going to show you now is a slightly better way to do that, and then I'm going to hand over to Mark, who's going to show a better way still, or another interesting way to do it. So here I've got little sporadic farm in my Jenkins. These demos are all very small, simple things, but rest assured, everything that we're going to see today scales to very large systems, including SAP HANA. If you saw me talking the last time we did this conference, you'd have heard some stuff about that. But nice simple demos just for the purposes of understanding. So I've got this sporadic farm. It's generating. We mark the tests that are flaky and we exclude them, and then we run them again and again to capture the failures, but we run them with recording, with live recorder in this case, where we're recording the execution of the program. So when we get our artifacts from those failures, typically your artifacts would be like some log files, if you're lucky, a core file or something. But because we're running this with recordings, when we fail, we get a recording, right? And this recording is kind of like a core file, but it contains not just the state of the program at the time it crashed or terminated, but it contains every preceding state as well, so you can go and see what happens. So I can take this, let's take this top one here. I'm going to download that recording, and I'm going to load it up into the debugger, which is going to look a bit like this. So this is my little program that ran in the test. I can see now, this is just like looking in the core file, right? So I can see it's done it's gone assert 0 because it didn't like something. Because cache, so square root cache is not equal to the correct value, should be 15. I can see I've passed into this function cache calculate, I've passed in number 255, and it's returned 0. So cache calculate's done the wrong thing, and I need to find out why. Now, if I were looking at a core file, I could do all of this, but then I run out, right? The information that I care about has gone. It's not in the core file. It happened some time ago in history. What I'm going to do here, though, because I've got, and I think you saw some of this stuff earlier today by the sounds of things, I can just wind the clock back. So we go back a line, go back another line. So go back to here just after cache calculate returned. And now I'm going to reverse step into, and I can go into that function and see what it did. And I can see it returned the ith entry of the cache. I this time is 80. So if I look at cache 80, I can see, sure enough, this contains bad data, right? So this is always a bad day if you're trying to debug this kind of issue. It tells me the square root of 255 is 0. All I know is that's not true. Someone at some point has stomped onto my data structure and put bad data there. I don't know whether that was another thread or a pointer error or a logic error. What I'm going to do here is add a watch point, which is like a super cool feature, right? So I'm going to watch the data. So watch point is a common debug facility. Of course, you run forwards until the data changes. What I'm going to do is run backwards until the data changes, right? So I want to know why that data is like that. I just set a watch point. I reverse back in time. So now I've gone back in time to when the data structure contained good data, right? The square root of 195 with integers really is 13. I can actually step forwards again. This is like watching a action replay if you're watching sports on the TV or something. Watch the data here as I step this forwards, right? Step, that's it. That's the corruption being written right there. So why is that happening? Or let me go back a little bit, see what's going on. So we're writing operand adjacent and square root adjacent into the cache, and I can see operand adjacent here is -1. You can't take the square root of -1, so of course it's garbage. Well, why has that happened? I'm going to add a watch point that, follow it back. Okay, operand JSON is being set to operand -1 and operand is 0. So here's my bug. I've gone, I called the function cache calculate with 0. It returned the right thing. It returned 0, but it left one element of my data structure in a bad state, and I didn't notice until some time later. And I can just set a watch point and go back straight to see exactly what happened. If you've seen any of my talks of these kind of things before, you may remember having seen that demo. I apologize for showing the same demo, but as I've shown many times, but I don't really apologize because I'm going to hand over now to Mark, who's going to show a different way to look at these recordings that I think is hopefully going to be quite interesting to the audience that we have today. So I'm going to stop sharing my screen. And Mark, you're going to take over, and I'm not going to be able to hear you, so I'm just going to shut up and let you go.
Thank you very much, Greg. I am just going to set up my sharing, so I just need to find the window out of my millions of windows that I'm going to show to you. So as that's coming up, I'll just say briefly, I mean, Greg's introduced. I was interviewed by him at the pub. I subsequently had an interview in his garden shed, which was a strange experience, but it was a positive one. It's led to a very interesting period of my career. So right now, my day job at Undo is as architect. So I have responsibility, in part, shared with other very, very talented people, for the structure of the product, for how efficiently the development team operates as a whole. And I try and do my bit to pitch in with anything the company needs doing. However, I also like to be lazy. And you'll have seen from Greg's demo that we have these tremendously powerful artifacts in our recording files. We've captured enough information there to reconstruct any intermediate state in a program's execution down to instruction level granularity. So you can step forwards or backwards by instruction. That happens to work very nicely in a debugger because we have all of the mechanics required to line up our behavior with the debug info that's provided, provide you with symbolic debugging, let you set watch points, etc. If I just fire up my example here, somebody shout at me if the text is too small, but I think this should be legible. This is actually a recording of the cache calculate program that Greg showed you, but it was done on my machine. And I'll tell you for free that actually we had a bad value in my example in cache element 90. So we're going to be playing with this. Now, although this is loaded up in the debugger, Greg has promised you that I'm going to do something a little bit different. The relevance to people here is that I'd seen a few years ago, I think, Facebook had prototyped some sort of SQL-based interface to some sort of system administration framework, so they could query stuff around their servers throughout their test farm. And an open source developer re-implemented it in terms of Postgres with some virtual table mechanics and some Python. I thought, well, if they can do that, maybe I can. And I am from, certainly from the perspective of the people in this audience, a bit of an SQL caveman. I find databases interesting from a distance, but I've never really fully understood them. So I'm afraid I might do a certain amount of disservice to things you know a lot better than me about. But ultimately, my goal was to create a query engine where instead of actually having to do what Greg's just shown and work through the recording and debug it, I would like to be able to tell an intelligent query engine what invariants I'm interested in, and for it to go away and figure out when they were violated and tell me about it. So I want to actually reduce my debugging from an active process of iteratively finding the source of the bug to just me being able to describe what I expected to happen, and the system tells me the answer. The reason I've brought up the Undo debugger first is because actually we're going to need some memory addresses. Because the prototype of this query mechanism I've built, which is called uQuery, doesn't currently have all the debug level niceness of symbolic debugging. So right now, we're going to be talking about register values, memory addresses, bytes. What we need to know for this case, we're assuming, I'm assuming we've identified at least what the cache element which contained the corrupted data was. For me, that's cache element 90. And its base address is 404.114. And actually, if we look at the fields in that, they are 1 byte in size. So they are 404.114 and 404.115. What I have in this other tab in my terminal is an invocation that's going to start the uQuery engine. Now, what uQuery is, it builds on a tool that we already ship with our product called Recording Converter, and that's able to convert the static portions of an undo recording, so the things that happened at known fixed times, into an SQLite database, which can then be loaded. What I've layered on top of that is an extension to SQLite, which this is going to start, which will also load the associated undo recording file. And what that has is enough information that if we instantiate it in our engine, we can do that instruction granularity reconstruction of everything that happened. So actually now we can start to reconstruct dynamic data and return it to the SQL engine to help it understand what happened during the history of the program. So just to demonstrate there's something in there, apologies, I'm going to reduce the text size slightly for a moment. We're going to select start from the registers table, and I'm going to limit this to the first 10 elements. And what we see here is the complete x86 general purpose register set. Along the top, we see the values arrayed. And on the left, we have this value called BB count. That is undo's internal time base. So this is how we express how far from one of these deterministic recordings you've progressed. The other table we have is mem, and that's frankly not very interesting. You're seeing values here from the start of time and from an invalid address. We're not going to be having much fun there. But what we can then do is say, okay, let's have an interesting address and see what's going on there. So we'll select from the memory table, which is going to be satisfied on demand by our engine, where the address that we're interested in is that number. And you can see at this point, the database is chewing away and it's generating vast amounts of data. There's actually about 500,000 basic blocks in here, so 500,000 rows per table. So we don't want to sit and wait for this, but I will just demonstrate that if I, oh, and apologies, I can make the text a bit bigger for you. If I set the start time to be somewhere slightly more interesting, so after libc is initialized and we've begun computation, we can now see spooling past different values of that number field that's in the corrupt cache entry. This is obviously going to take a while. We could sit there and we could actually just specify queries like this and say to SQLite, you know, fetch all these data values, tell us interesting things about them. But actually, there's a further insight we can have here, which is that ideally, we don't want to do that. We don't want to generate 500,000 rows that are probably going to be filtered down into not many interesting results. So we want to cut down our search space. And actually, the way of doing that efficiently is to exploit the hardware provided watch points mechanism, just like Greg showed in his debugging demo. So in order to supply that, we also have available in uQuery a mem changes table valued function. So what I'm going to show you here, this is the previously mentioned value memory address that contains the square root values. If I select from memory changes on that, what we get is a time series throughout recorded history of the different values that square root value has seen. And so, I mean, spoiler here, we really know, because we've seen Greg's demo, that the value at the end is going to be the corrupt one. But let's assume we don't know, or let's assume that the corruption's sporadic, and that sometimes the cache may have corrupted and then come good again if we didn't reference it and the bad value got evicted. So we might want to specify a little bit more generally to the query engine what we're actually after. And what we're actually after is, please give me the times this cache entry didn't look like a valid integer square root. So if you'll bear with a bit of rapid typing, and bearing in mind I'll probably get it wrong a couple of times, we'll use a CTE and we'll say, get me all of the values of data, which we'll call number, from history, where we have 404.114 as the address. So that's the address of the number field in that struct. And then we'll also have the changed values of the square root. So this is the interesting points in time, basically. We're filtering down on when that watch point fired, which enables us to cut out a whole load of search space and construct a more efficient query. Need to be very careful not to type the wrong thing here, as I've done in the past. We'll see in a moment. But basically what we want to do is say, get the number series of all the numbers in history, natural join it with the change series of the square root values. And then for completeness, let's ask it to solve our problem. So let's say the number has to be greater than or equal to its integer square root, and it has to be less than, or well, just less than its square root squared plus 1. Did I say greater than its square root? Obviously it does, but the square of its square root. Let me just fix my select syntax. Proves it's live, as Greg always likes to say. And if anyone wants to shout out where I've typed in the syntax wrong, they are very welcome. Sorry, I heard an echo there, but I'm not sure who it's from. Oh, I'm afraid. Thank you for saying things, but you're coming through very, very quietly for me, and I can't quite make it out. Right. I think I've just figured out what you're saying. You're saying I've got a comma in the CTE where I shouldn't do. Yes, I have. So one moment. Drop that comma. I wasn't really expecting to miss a bracket. Let's get the where out. Whoops, I need to also be selecting the BB count. I think I should have a BB count, really. Ah, and I've also missed a from. One moment again. With number series as all of this stuff from somewhere that makes sense, where the address is something we want, with the square root changes coming from the memory changes, yes, with selecting everything we wanted from the natural join, where the square root makes sense. Bingo. Finally. Hey. So if I just pop back to my terminal and we go to that time in the recording, print out our cache element. You can see it's got the bad value in it. We go to the previous. We go to the previous location. Print the cache element. It's got a good value in it. And so we've used this to solve our problem. And actually, the query has run in less time than it would take you to run the debugger. The really cool thing, and I'll just leave you with this as a parting food for thought, is if we can get this and we can query this information across all of the history in the debugger, we can actually use this not just on the flaky recordings that Greg's mentioned, but as an internal consistency check, even on parsing tests. So we can actually automate the process of looking into an application from the outside and effectively doing asserts, but without having to compile them into the code. And I'll leave you with that thought. Thank you very much.